All right, so I was saying that we need to start lab 2. Lab 2 in terms of, I don't want to call it the theoretical background because it's not really theoretical background, but it's the background that would help you know what to cover in the experiment itself. So basically the lab report and explaining what to measure and how to measure and how to proceed, along with some theory when needed. This is one. Then we need to watch the video, but we're gonna watch only pieces of it. You can watch it later, I suppose. I'm gonna pause over very important sections to explain few things. And then we have, if I'm not mistaken, we have an appendix to the lab. It's all in the PowerPoint that I'm gonna share with you. We will edit this PowerPoint definitely. So the appendix I'm talking about is the last slide, where I want us to do some work together as a practice or a warm up before the lab report, which is to plot something, find the slope and find the error on the slope. We will do it as a team and you will submit your answers just right now on the chat. It will be a good warm up before the lab report, okay? So let me start with the actual lab. Lab number 2, capacitance and dielectrics. You can see my screen, I suppose. So before I start lab 2, I need to tell you the way I shared the results for lab 1. I did not like it at all because lab 1 was descriptive. Most of the questions were open-ended and it was confusing for a lot of students. You cannot imagine how many emails I answered and how many WhatsApp texts, and I'm not done yet. I suppose maybe I did not answer your question yet because I still have questions coming up. So the results were not done by me, and I don't agree with many of those results. So from now on, the results have to be clear. For capacitance and dielectric, I'm gonna give you the values, and when you have values, it will be so much easier than a map, you know. And I just recorded a lab, maybe lab number 4. Is it lab number 4? Yes, it's lab number 4. I did all the experiments in front of the camera, which means you can watch the lab and write down the observations without me telling you these are the observations. So that would be ideal. The lab was not long, maybe 17 minutes. I did it so quick, so I talked without breathing, you know, just for it not to be too long. And I did all the steps, and you watch the video and write down the observations. I think that would be much better. Maybe I cannot do that for lab 1 because to give you the coordinates, it will really be time consuming. Anyway, so lab 2 is not descriptive. You will have a table of results. You need to plot and do calculations. It's gonna be less confusing. This lab is made of 3 parts. And as you can see, the lab is long, like 3 parts. Part 1, you will study how the capacitance will change as a function of the plate separation. Doesn't look difficult. Experimentally, you change the separation of the plates, you measure the capacitance, that's it. Now the lab report, you would need to plot and do linear regression, find the slope, the error on the slope, and then deduce epsilon 0. This is time consuming. Now part 2, effect of the dielectric. Experimentally, it's easy, and lab report is easy because you just have to insert dielectric measure with dielectric, without dielectric, that's it, and do simple calculations. Part 3, the experiment is long, but I would do it. You will have the results. The results are so easy to deal with. You just have to do some calculations, no data analysis. And the 4th part, the experiment is short and easy, and the calculation as well. So once you're done with part 1, I think you're done with 60% of the lab report. Okay? All right, now part 1. This is part 1. You will be given a device very close to this one. To find the capacitance of any parallel plate capacitor, you follow the equation C is epsilon 0 A over D. I need somebody, maybe Bashir, to explain what C is. Bashir, are you with us? No, Jana?
Yes, doctor.
Bashir, good morning, Bashir. So
good morning.
Bashir, good afternoon, actually. What is capacitance? How do you define it?
I don't know a definition for it, but I know the formulas.
Okay. Can you see my camera? Can you see this bottle?
Yes.
Do you think it has a capacity?
Yes.
Okay, I can tell you it's more than half a liter. I think it's 0.75 liters. We say it's a capacity, not a capacitance. It's the volume actually. By the way, it's still full. I did not drink today, so you can blame me.
Okay.
Yeah. So basically my question is, do you think I can squeeze in more water inside?
No,
Why not?
because it's already full.
And we cannot squeeze water in the liquid state. If it was a gas state like water by vapor, I would squeeze it and increase the pressure and squeeze more water particles inside. So water in the liquid state cannot be compressed, and therefore I cannot squeeze in more particles. For the capacitor, I can squeeze in more charges on the plates if I apply a stronger potential difference. Remember, the potential difference is basically in electric pressure. So by definition, C is how much Q you can store on one plate as a function or per potential difference. Let me call this delta V. So let's say this is 2 coulombs, and 2 coulombs are basically 2 farads. Okay, 2 farads. And farad is basically coulomb per volt. Okay, which means if I apply 1 volt, I can store 2 coulombs. If I apply 2 volts of pressure, I can store the double amount, which is 4 coulombs, you see? So capacitance is very similar to the capacity of the bottle. As long as the more pressure I put on the liquid, the more particles I can squeeze in a certain container that I'm gonna call here the plates. All right, Bashir, the question for Tia is, Tia, how do you measure the area of the plates? What is A, the area of plate 1 or plate 2 or both, and how do you measure it? Tia? Not here? Maybe Jean?
Yes.
Tia, okay, Tia. What is A? How do you define A? So the question is, how do you define A and how do you measure it?
Honestly, I don't know.
Can you try? Shoot something, even if it's wrong. A is the area of what?
Is it the area of the plate?
Yes, I remember from grade 11 we say...
Can you hear me?
Yes, I can hear you. You're glitching a bit, but I could hear you. So the area, we usually say the common area. Like, for example, if you have this disk for plate 1 and plate 2 is this, for example. So we take the common area, the part facing each other, this one. But these 2 plates will be perfectly facing each other. So the common area is going to be the whole thing. And to be able to measure the area of a disk, how do you proceed experimentally, Tia? What measuring tool do you need to find the area? Maybe Jana can help Tia?
Yes, can you hear me?
Yes. Jana speaking. Yes, Jana. Jana, how do you measure the area of a disk? What measuring tool do you need?
Ruler?
Yeah, a ruler. What do you measure with a ruler?
You measure the radius because it's pi r squared.
Okay, so you do pi r squared. You need the radius. How do you measure the radius if the center is not visible?
We can measure the diameter and then divide it by 2.
Yeah, good idea. And keep in mind the smallest subdivision for a regular ruler is 1 millimeter divided by 2 is 0.5 millimeters. So you need 1 decimal in case you're measuring in millimeters. If you're not sure about the center and you're not sure about if the diameter is this or, you know, you can measure the diameter many times and find the average, because some students would have difficulties. Or you can guess what is the longest chord to be the diameter. So maybe I'm gonna give you the diameter and you do the calculation for the area, maybe the uncertainty, and you do the calculation for the uncertainty. Keep track of this. So here, your job is to measure, this is D, the distance between the plates from the inside because the plates are thick. I think, yes.
So what's the equation here for the area? Pi r squared?
Yeah, area of a disk, pi r squared. Let me write it down.
Okay.
Pi r. By the way, I'm gonna share the edited PowerPoint, not the initial one, the one that is edited. So R is the radius. So let's say centimeter squared, you'll end up with the meter squared, centimeter squared and centimeter for radius. And if you know the uncertainty on the radius, you can do propagation of error to find the uncertainty on the area. Okay, keep that in mind. All right, so here
Can I ask a question?
Yes.
What if will it be given in the plates or discs? Because couldn't they be like rectangles or parallel plates?
Say it again.
The parallel plates of the capacitor can have multiple shapes.
True.
Is it given in this experiment that they are discs?
Yes. So this equation can be used for any kind of parallel plates. In this experiment, they are discs, and they are given to be discs and perfect discs. I will show you the video, and you will see they are beautiful discs. Okay?
Okay.
All right. So yeah. So D will be the distance between the plates. You will start from 5 millimeters and take the measurements. You will connect the plates of your capacitor to an LCR meter. An LCR meter looks like a multimeter. It gives you the capacitance in farad, and it's very precise. It's a digital measuring tool. So the smallest subdivision will be your uncertainty. And you will vary D, the plate separation, you will measure the capacitance. And that's it. But there's something you need to be careful about. If you measure the capacitance of those wires without connecting them to the capacitor, it will give you a very small value that cannot be ignored. So you have to make sure you minus this value from the whole measurement. Okay? I'm gonna show you exactly in the video how it is. So basically, so now my question for Joe. Yes, Joe. Joe, if I plot C, yeah, if I plot C versus D, do I get a linear relationship?
No.
No, because they're not proportional. What do you think I should plot to get a linear relationship?
1 over D.
Okay, so C versus 1 over D. And you will get some scattered points, but they would look linear in a way, and you will do the best fit to find the slope. Now, what does the slope represent? Using this equation, this to be your Y and 1 over D to be your X, what would be your slope?
A?
So,
No. One sec.
So C is your Y.
This one, the 2 is to A and epsilon.
Yes, and Juliana is saying it's epsilon 0 times A. That will be your slope. Yeah. Anybody knows the value of epsilon 0, the theoretical value? Let me write it here.
That's 8.85 times 10 to the minus 12.
8.85 times 10 to the negative 12 used with SI units, right? Is that what you said?
Yes.
Okay, let me just fix it a bit so we can keep it. So in this part of the experiment, when you do the plot, you will be asked to find the slope, and from the slope you deduce epsilon 0. You say slope is equal to epsilon 0a, you find epsilon 0, and you compare it with the theoretical one. It's going to be close, but not too close, because this is the case where you have vacuum between the plates, and in your case you don't have vacuum, you have air. With some humidity, depending on the weather and depending on the AC, if it's on and off, and LAU, you know the location of LAU, because we did this experiment in this lab. And maybe you will have some errors on the C level. C, the capacitance. So it depends on your measuring tool for the capacitance, measuring tool to find the radius and hence the area, measuring tool to measure the distance between the plates, and all these would give you an epsilon 0 not too close to the theoretical one. That's part 1, and yes, it's time consuming, but not difficult. Part 2 is super easy. Now the same plates, you measure with dielectric, then remove the dielectric and keep the distance same. So this is a constant. So measure without dielectric and with dielectric. Let me call this CD. CD stands for capacitance with dielectric. Your job is to find K. How do you find K? Jennifer? So Jennifer, I need a method to find K from the following procedure. If Jennifer is not with us, maybe Jean can help. Okay, Jennifer, her microphone is not functioning. Jean, can you proceed? Okay, so Jennifer is saying we get C. Okay, let me show you. Where's the thing that I'm sharing? Okay, I'm gonna fetch the chats. All right. Anyway, so Jennifer, you can keep on typing. We can divide C by CD. Okay. So basically, what Sherbel and Jennifer are saying, since you measured C and you measured CD, you simply do CD, which is the capacitance measured with the dielectric, divided by C. Since you have the same area and the same distance and the same epsilon zero, they do cancel out, and you will be remained. This is the remaining for the calculation. So by simply doing the ratio, as long as you measure the capacitance with and without the electric, without moving the distance between the plates, it's gonna work. Now the question for Bashir or maybe George. George, I did not talk to George yet. George, I'm gonna give you an example for C. Let's say I measure C with the dielectric to be 282.4 nano. It's gonna be pico, by the way, because pico is really small. So back to you, George. What this is measured by the LCR meter, and the LCR meter is a digital measuring tool. What would be the uncertainty on your digital measuring tool? Maybe Sherbet can help.
0.1.
0.1 picofarad. Definitely. Can you explain why?
Because I have one decimal place when I took the measuring, so it should be it's a digital شو هو؟ measuring tool. Okay, so it's 0.1.
All right. So
it's the least digit.
Yeah, since you're dealing with a digital measuring tool, the smallest subdivision is the last digit, and you just add 1 because it's the smallest digit. So CD will be measured, you will be given the uncertainty, C will be measured and given the uncertainty. Your job is to calculate K and the error on K. I would want to ask Farah how to calculate the error on K, or how to do the propagation of error. So the question again for Farah, and the question is, I want to find the error on K. Yes, Farah?
Doctor?
Yes.
You mean Farah Abdul?
She's not here?
No, she left uni.
No way, but she's still on my blackboard.
Yeah, but خلص.
يا الله زعلتني. Is she okay?
Yeah, she's fine.
Okay, say hi to her if you're talking to her. Maybe I'm gonna ask Yara.
What's up?
How many times I told you that my daughter is Yara? Like 1 million times? And Yara is very difficult to handle. كتير بتعذب. وين Yara? She's absent. Maybe I can ask Margarita. Or maybe I can ask Dana. Or
Hi,
okay, who's this?
Dana.
Okay, so Dana, my question is, I want your help, please. I have the function K to be CD over C, and I want to find the error on K. So you can see I have two parameters and like two measurements, both of which have an uncertainty. So I'm gonna create a big radical, yeah, and two parentheses like this. Help me out, please, with the derivatives. How do you proceed?
First of all, the derivative of that CD times the error on CD.
Okay.
Plus squared, plus the error on C, the derivative of C plus the error times the error on C.
Okay. Okay. All right. Now help me out with the derivatives. How do you find this derivative? So CD is your X. So K can be written as X over a constant. Say it again.
1 over C.
Yes, 1 over C is the answer. Now, how about this one? If C is your variable, like constant over X. It's gonna be constant over X squared with a minus.
Okay.
Right? So again, if you have constant over X, the derivative is gonna be minus constant over X squared. Okay, I know that you basically forgot this. That's why I'm giving you a reminder. All right, so for this part of the lab, you only need to measure with and without for 2 types of dielectrics and find K and the error on K. This would take you around 10 minutes, not more. The third part of the lab, you will be given many capacitors. By the way, I remember we discussed that with the other class. What is the difference between nominal value, measured value, so measured value and calculated value? Maybe value, maybe I can ask Elsie to speak up. And if not, Elsie, Jean. I saw Jean joining us.
Not really sure, but I think nominal value بتبقى مثل high or low, medium. Measured value بتبقى using a ruler, so we get the value or something. And calculated value, we use a formula, so we get the value.
All right, obviously, thank you, Jean. Obviously, the calculated value is what you calculate. The measured value is what you measure with a measuring tool. In my case in here, if I need to measure C2, I use the LCR meter and I measure C2. The nominal value is basically what is written on it. And I never ever trust this value, because if it's written on a 2 microfarad, the measurement is gonna be different. So the nominal value has a very super low precision. I would say accuracy, not precision, or both. And now my question for, I don't know, maybe Ahad, is if they ask you to compare 2 values and basically you were asked to find the percentage difference, can you please remind us quickly, how do you calculate the percentage difference?
Yes, doctor.
Yes, how do you do it? The percentage difference. Let's say I want to compare the calculation.
Can you hear me?
Yes, I can hear you. So the question is, compare the calculated value to the measured value. Is it that you're talking and we can't hear you? Maybe Maria can speak up?
I have very bad connection. I can't hear you very much.
Yeah, I'm sorry for that. Maria, maybe can ask? Or Anthony? Or Sherbel?
We do the measured value minus the calculated value over calculated value times 100.
Okay, so I'm gonna start with absolute value. Yeah. Then I'm gonna do the difference between measured minus calculated divided by calculated, and all this times 100 definitely. If I want to, you can keep it as a fraction, but 100, like to make it percent, you multiply by 100. So I'm gonna take the calculated to be my reference. So this is how I compare measured and calculated. Usually I never compare with a nominal value. So those two is what I compare. So what do you have for this experiment? You will be given a box of capacitors that you will see in the video in a moment. You will see nominal values, but you will simply ignore them. Just keep them like names of your capacitors. You measure each, then you plug them in parallel or in series. You measure the combination. That would be the measured value. Then you calculate. I'm gonna ask somebody or anybody who would like to talk. Let's say I give you 2 capacitors. One is a 22 nanofarad and C2 is equal to 44 nanofarad. And if you put them in parallel, how do you calculate the C equivalent or the total C? What do you do? So in parallel, how do you find C equivalent?
Just we add them.
We simply add them. So you do C1, C2. Okay, what's wrong with 1 and 2? Yeah, we sum them up. So we're gonna end up with 66 nanofarad. Now my question is, if they are in series and you are asked, what's wrong? Okay, and you are asked to find C equivalent, how do you do it? Yeah, it's on the table, you can see it. So
1 over C plus 1 over C.
okay, so you do the parentheses C1 to the power -1 on your calculator. Please do it. Get ready with your calculator and scream the answer if you have it ready. And you do -1 to the final answer. What's the answer for this one? Anyone has an answer? I'm getting my calculator. Who's faster than me? 44 over 3, Jennifer. So 44 over 3 is gonna be 14.67. I'm gonna write 15 to keep it with 2 significant figures. So 15 nanofarad, okay? Cool. So basically you do the calculations, I do the measurements, and you compare by doing the percentage difference. This part is gonna be easy. Now the last part, part 4, you will be given BNC cables. They look like this. These are coaxial cables, like you have a cable outside and a cable inside. You see here the copper, it's the outside cable, and there's a copper wire inside, and you have an insulator in between, exactly like a capacitor. You have a cylindrical plate outside, cylindrical plate inside, and you have a dielectric in between. To find C, you need to measure, actually you measure C with your digital measuring tool for C. You measure L, the length of the wire, with a ruler. B and A, you simply measure them, or they are given to you. B is the radius of the first cylinder, and A is the radius of the inside cylinder. And this way you can simply calculate K, okay? But here you will have your LCR meter. You will connect the first cable to the LCR meter. You need an adapter to be able to do so. So make sure you measure the adapter alone first, then adapter and wire to be able to minus the capacitance of the adapter. And then you need another adapter to connect wire number 2, okay? And make sure to do enough measurements, or to consider the measurements given to you to minus adapter number 2. Like I will do the measurements with adapter number 2 and without adapter number 2. So you can guess what is the capacitance of adapter number 2, which means your job eventually is to know C1. So this is what you need to measure. You need to measure C2, and you need to measure C total minus the adapters. So you should know C of the adapters. Now that you have C total, your job is to guess, is the connection, I'm talking about this connection, is it a series connection or a parallel connection? Because you don't know really what's happening inside. So you have a cable outside and a cable inside. By connecting them as such, is that a series connection or a parallel connection? C total will let you know. So you can use those to be able to tell if you did the sum of the C's or the inverse of the sum of the inverse of the C's. So this would help you guess if this is a series or a parallel connection. Okay?
Doctor,
Yes.
can you repeat part 4 again? شوية ضعنا.
I know. أنا كمان ضعت بحالي. So let me say it again. You have an LCR meter. هلا on the video you see. You measure أول شيء adapter number 1. Let me zoom in and show you. There's no way you can connect this to the LCR meter, so you need a special adapter. You measure adapter number 1. Then you connect the wire. Let me call it wire 1. So now you measure adapter plus wire. To know C1, you minus C of the adapter. Then you measure adapter 1, wire 1, adapter 2. You already have adapter 1 and wire 1. You can minus from your final result to get adapter 2. Then you add wire 2 and you measure everything minus this value. So you can tell C2. So myself, I'm gonna give you all the measurements. Your job is to guess C1, to guess C2, and C total is gonna be everything minus the adapters. Now that you have C1 and C2 and C total, your job is to guess if this is a series or a parallel connection. Does it sound easier? If not, let me show you the video, okay? All right, now for the video, you have only, it's under recordings, you have only one recording. I hope it's gonna be quick, but anyway, I'm gonna make it fast, okay? And jump some sections. In this experiment, we will explain capacitance and dielectric constant. What equipment do you see on the desk? You have a capacitance box on which you can read what the condensateur. You can see many capacitance. So these are the nominal values written on it, okay? You have a capacitance from Pascal of a variable distance between the plates, and you see each plate is made of a disc. So a circular plate. And you can see you can vary the distance easily. Make sure to measure the distance between the plates. You have the LCR meter. The LCR meter measures LC and R, which is the inductance, the capacitance, and the resistance. So basically, I'm using this one to measure the capacitance of a resistor. So it's very precise. You have a multimeter that could be used. Okay, this multimeter will not be used for this experiment because no need for it. It was here by mistake. Potential to calculate, to measure the potential difference. Why do we need it though? I don't think we really need it for this experiment, so let's keep it aside. Those are two dielectric, the material of which is unknown. Both are plastic, one is thick, one is thin. So maybe you can compare both. Okay, it says plastic, but you know you have 1 million types of plastic, so it's unknown basically. We have some banana wires, maybe 4 or 5 banana wires, I don't know how many. We have some plugs for the LCR meter that you can use. You have the LC cables of different thickness, maybe, yeah, and some adapters, okay? As you may have noticed, the experiment let me show you quickly how I do the connections. I'm gonna connect my LCR meter to the capacitor, okay, like this. The distance between them will actually change your measurement. So if your measurement, if the cables and the capacitors, the plates are not moving, everything is rigidly fixed, you should have a constant value whatsoever. So I can read 13.3 picofarad. Don't forget to minus from this value the initial measurement of the cables. All right, so your job is to have a distance between the plates equal to. So as you vary the distance, the measurement of C will be different. I would want you to see this part. Take the measurement again. This is the, okay, let me keep them apart. So here I'm measuring the capacitance of the wires not connected to minus this answer from all my measurements. 1.3 picofarads. So you will ask me the following question. If these cables were close, you see the measurement would be a little bit different. By the way, the difference is not huge. We're talking in the picofarad, and picofarad is downstairs. You can watch this alone. Now I'm gonna show you how I'm inserting the dielectric. Put it between the plates. Again, I need to make sure that this is connected. Let me try to put it in the picofarad. Now your job is to close the capacitor in such a way that you have no air between the plates. So you're not supposed to be compressing the dielectric, and you're not supposed to have the plates loose or spaced, and you will have extra air in between. So make sure when you remove the dielectric, the distance between the plates is made not to vary at all. So with the dielectric, you do the measurement, and without the dielectric, you will do the measurement again. So the point is to see that D is a constant. All right? So that's it. And then now I'm getting ready to measure the capacitance of this box. Yes, play. one of the capacitance, and this one to this one back to one of the capacitors. You will notice that the nominal values are written on the box, and the unit is microfarad. Again, microfarad is 10 to the negative 6. Picofarad was 10 to the negative 12. So this is 1 million times bigger than the values we were having, or more, you know. I just want you to be able to compare, which means I will expect my SCR meter to change its unit. All right, let me continue. So I'm measuring C for each, and then I need to connect them in parallel. A current flowing in the circuit. So this is a series connection, because maybe show you again how I did the connections. Okay, check. In series, what do? I put my capacitor, my SCR meter as such. So I will have a wire going through the capacitor. Then I need to connect these two together. Let me try to do so. Okay, so if you imagine to have a current flowing in the circuit, it will go out from this terminal into the first capacitor, to the second capacitor, back to the LCR meter, and obviously this shows a series connection. So what measurement I will have here, it will be the equivalent capacitance of both capacitors C1 and C2 in series, along with the capacitance of the wire that I suppose is negligible in this case, so you can just ignore it because it's in the picofarad and all the measurements you are doing are in the microfarad. So minusing this answer from your measurement will do no difference whatsoever. All right, so here this is a parallel connection. I can connect the LCR meter to one of them. The LCR meter will be measuring the total or the equivalent capacitance of my connection, of my combination. So what you read here is not C1, neither C2, but C equivalent. And you will continue doing, and so on and so forth. You will be asked to connect C1, 2, 3 in parallel and in series and create random combinations, do the measurements. Eventually, they will ask you to calculate as well C equivalent to be able to compare your calculated value to the measured value also. So that's it for the third part. All right, let me show you now the BNC cables and how to connect them. Let's have a look at those cables. It's a long cable. Your job is to measure the length of this cable before you start. And you can see that this is a coaxial cable. So you have a cable outside, a cable inside, exactly like the case of the banana wires where you had two separate cables. So this is a coaxial cable. If I may measure the capacitance of this cable, I need an adapter. So I'm going to take the SCR meter. I hope it's visible on the camera. I can use this adapter, connect it into here, and then connect the cable. And make sure the cable is straight somehow, because you don't need to trigger some distance variation in both. So make sure. All right, so you see the adapter, measure the capacitance of the adapter first, then adapter plus wire to be able to minus the one of the adapter. Your cable is elongated on the desk. Put your LCR meter on. Wait a second for it to give you a certain value. You see, it's 96.6 picofarad. Picofarad is a very small value for the capacitance, and therefore I would think maybe that the capacitance of the adapter will be affecting my measurement. After I write down this value, which is the measured capacitance of my first cable, I will make sure to measure the capacitance of my adapter and minus this value from all my measurements. You will also have to repeat the same thing for the next cable, for cable number 2, measure the length and the capacitance. Eventually, you will be asked to connect both cables together. So this is a female-female connector. You will connect the first cable to the second cable and connect both to the adapter, like one terminal to the adapter. Maybe do this experiment on the floor to elongate the cable. Yeah, so you need the cables to be really really straight to be able to do the measurement as long as you can. And what you will measure here, okay, in this case, I did not get any measurement because it was going down from the table to the floor. So if you repeat the experiment and make sure they are straight, you will end up with a measurement. Let me see.
Doctor?
Yes.
What about that thing that's connecting both wires? Doesn't have a certain value as well?
It does. So how about you measure adapter 1 plus wire 1 plus adapter 2? That's it, to deduce the value of adapter 2. Okay, Bala, you have to minus the C of this adapter. All right,
Okay.
and it will be given to you. So I'm gonna give you C of adapter 1 plus wire and adapter 1 alone. You deduce what you need. Like I'm gonna give you a set of measurements and you will be required to fill in a certain table. Okay, it's not gonna be difficult. This is simple.
Okay.
Maybe talking about it is more confusing than what it is actually. All right, so that's it for the experiment. I will definitely share the link so you can watch it slowly, but I wanted you to see quickly what it will be about. Meanwhile, I want us, before we leave, to try this part. This part, you are given a set of measurements. So this is a warm-up before the lab report itself. I'm gonna give you some time, maybe around 10 minutes, not more, to do the plot yourself, to do linear regression alone, find the slope alone. Maybe you can throw out your answers on the chat. Make sure it's private chat, not public, so not everyone can see your answer. I'm gonna keep on sharing my screen, maybe do the work slowly on Excel. You can watch me and you can do it alone. And maybe we can come up with some answers. How do you feel about that? Okay, I'm gonna start. So every time you have an answer, put it in the chat privately.
Doctor?
Yes.
Just one question. Do we keep it the same units or we have to convert?
It's a good question. I would be really not happy to play with 10 to the negative 12 and 10 to the negative 3. For me, I would want to keep as it is, as long as I show the unit well.
Okay.
Okay, I'm gonna stop recording. And